So starting from the point where we have left in the previous video, example 1, and what does it says in example 1, that construct the influence line for the vertical reaction at A on the, okay. So we only have to determine the vertical reaction at support A of this beam, and you know the procedure. Just move the load either from support B to A or from support A to B. And if you are moving load from B to A, then the equations we have discussed previously. For example, let me show you for example, this. If you are moving the load from right to left, okay, right, like this we discussed in previous video. If it is moving from right to left, then for RA, this will be the equation, which is x by L. And if it is the other case, for example, the load is moving from A to B, then this equation will be for RB, and for RA, this will be the equation L minus X divided by L. Okay, so please keep in mind that what you are using, the only thing you have to know is that the concept. You know the concept, then you can solve everything. So in this case, the load is moving from A to B. So I'm taking moments about B is equal to 0. Summation of f of y is equal to 0. So minus A into 10. See, uh, it has taken counterclockwise as positive. So this A is making clockwise movement about point B. So minus A into 10 plus this 1 is producing counterclockwise movement into this 10 minus this 2.5 is 7.5. So from this equation, the AY is 0.75. Okay, so you can just put different value of X. For example, here it can be 5, it can be 10. You will get different values of AY. Okay, see, for example, X is equal to 5, you have put it 5, so you have got different value of AY. So in this sense, you can create a table. See, in where by varying the value of X, the value of AY is varying. Okay, so you are getting maximum value of AY when load is on the support. When the load is at support A, all the reaction is given by support A, and reaction by support B is 0. So as the load is moving away from support A, the reaction is reducing. How much reducing? It is reducing like this. Okay, when it moves at half of the distance, half of the reaction is provided. So you can see that the equation is L minus L by X. See what we have discussed in the previous video. Okay, you remember, and I've just shown you. See, L minus X by L. Okay, so here the general equation is minus AY into 10 plus 10 minus X into 1 is equal to 0, and putting the values and solving for AY is 1 minus 1 by 10 into X, right? Just multiply this value or this influence line diagram with the magnitude of the load, and you will get it for that prescribed load. Now example 2, construct the influence line for the vertical reaction at support B. This is the support B, this is a overhanging part, and this is the pin support. So the support, sorry, the load is moving from A to B and then further to this point. Total is the total length of the beam is 10 meter, where this span is 5 meter and the overhanging span is 5 meter. Okay, so the load is moving from 0 to 10, and you have to determine the reaction at B. So first, the load is between A and B, and second, the load has passed beyond the point B. So what will be the equation? The equation will be summation of a movement about A is equal to 0 by into 5. See, by into this 5. See, we have taken moment about this point is 0. So by into 5 minus 1 into x. This 1, and it is at the distance s. So you have using different values of x, and it is producing a bending moment about point A in the same direction. So by is equal to x divided by 5. Okay, So now put different values of x. For example, when x is equal to 0, the load is at support A and reaction at B is 0. And as it is moving beyond, so the reaction at B is increasing. At a distance of 5, the By is equal to 1. Okay. And when it is moving beyond, so the reaction is double to that of the load. Why? Because there is a bending moment included in it. See, when the load is at this point, so the reaction at By is 2 times to that of this load. Okay, because one kip is the reaction and one is the reaction due to the moment, because this one kip or one unit is producing a bending moment of 5, and this these reactions have to produce a counterclockwise bending moment. So at A there will be a negative load and at B there will be a positive load. So 1 plus 1 2. Now in example 3, construct the influence line for the shear at point C of the beam. Now this is point C, which is 2.5 feet from the support A, and you have to construct the influence line diagram for shear force at this point. So the load will be varying along this length of the beam, and you have to determine the maximum magnitude of shear force. Okay, so apply the load at point C and determine the reactions 0.75 and 0.25. I think this step is the most simple step. Now take any side, either side of the beam. See, for example, the left side or the right side. So if you are taking the right portion of the beam, you know that the plus upward shear will be positive. Okay, so there are two conditions when you are taking section just to the right of the load, so that the load is not added in the section, and the other is when you are taking just to the left of the load. The section is same, but in one case you are including the load, and in the other case you are excluding the load. So first you are excluding the load, there is only reaction. Just take summation of f of y is equal to 0. Vc is also in upward direction and the reaction is also in upward direction. So Vc is equal to minus 0.25. It means that the shear force is negative. Now when you are including the applied load, okay, for example this is the case. See, this is everything is same, you have just included this one unit load. So summation of f of y, the same equation. Now 1 is downward, so minus 1 plus vc plus 0.25, so vc is equal to 0.75. So in this case vc is positive. So at the same point C, you have seen that the shear force has changed from minus 0.25 to 0.75. So this was the point of variation. See, here your shear force has changed from minus 0.25 to 0.75 at the distance of 2.5. Okay, so this is your shear diagram, sorry, influence diagram for shear force at the point C, right? And this is your equation. For example, Vc is equal to minus 1 by 10 of x in this portion, and Vc is equal to 1 minus 1 by 10 into x in this portion. So from 0 to 2.5 you will be using this equation, and from 2.5 to 10 you will be using this equation. Okay, and putting the values, you will be getting these values, these results for Vc. So this is your shear force influence line diagram for shear at point C. Got it? Similarly, the same thing can be plotted if you are using this left section. Okay, so in right section, upward shear will be positive, and in left section, downward shear will be positive. So you know these things, and this is how the equations have been derived. Now example number 4, draw an influence line for the reaction number 1, shear number 2, and moment number 3 for both points A and B using the tabular method. Okay, so this is your cantilever beam of 10-meter length. The the point B is at a middle of the beam, right, at a distance of 5 meter, and it says that draw reaction, shear, and moment for both the points. A is the support and B is the middle of the beam, right? So influence line for the reaction at point A. Since all the reaction is provided by the support, so this will be your influence line diagram. 1, and it will be going straight. See, here if you are making an equation for this, you will get that by varying the distance, it won't affect uh, the reaction. Okay, so no matter what is the case, wherever you apply the load, all the reaction will be provided by the fixed support. Okay, now influence line for the bending moment at point A. So at point A, when the load will be applied at the farthest end, the bending moment will be maximum at support. See, you know this thing, right? So if it is applied here, you will get the maximum bending moment. When it is coming close to the support, the bending moment will be reducing, and when the whole load is applied at the support, there will be no bending moment in the beam, right? And similarly, no moment will be resisted by the support. And similarly for the shear force, when you are applying the load, point load at this point, the shear force diagram will be like this one. Okay, so all these were for was for point A, and this is for the point B, right? That if point B is resisting the load, so this will be the shear force in the beam. Similarly, the influence line diagram for bending moment at point B. So the bending moment up to this here, the bending moment is 0 and is increasing from point B. Okay, so why calculating moments is important? Because if you are not calculating the moment correctly, then you can cause the complete collapse, see, of the structure. The crane which was not designed have which was not properly designed, for example, in the case, so the car couldn't be supported by it and it dropped down. Okay, so there can be a lot of examples that why calculating the bending moment is important, because the capacity is very important, but first you have to know the demand. Okay, so analysis is what you have to determine the demand on the structure. So the case here is that you have brought some crane to bring out the things just fell into the sea or river, whatever it is. This is the next step. Okay, you are pulling it out of the sea or a river. This is your crane. You are taking it out, and boom, you have just your crane is also gone. So this is why it is important that you have to calculate bending moment very carefully, right? Now the crane you had brought to take out the other thing is also there, and you have to bring it out. So you have brought a bigger crane. See, it is much bigger than the previous one. For example, this one, and you are applying the your all the efforts to take it out. See, this is your bigger and stronger crane system. See, it is bringing out the cars and the crane. Oh, and what happened? See, it has gone. So, this is not in your lecture, but you have to know that how to calculate the bending moment. You have to figure out the important steps and all the necessary data required to calculate the moment capacity and moment demand on the structure. Then you will be able to uh, design the structure with the required performance levels. Okay. Okay, so there is a second method which is called qualitative method, also known as Muller-Breslau's principle. The previous method that we discussed was quantitative method, in which we were determining the quantity at each and every point, right? And it was a lengthy process. The second is the qualitative method. We just draw the diagrams directly without using equations. What are the steps? For example, in support reaction, remove the restraint in the vertical direction. If you want to determine the reaction, So reaction in is vertical direction, right? So it says that remove the restraint in vertical direction and only restrain it in horizontal direction so that the beam can freely move in vertical direction and induce a unit displacement in the direction of the reaction. So the reaction is in upward direction, so induce a displacement and it will move upward. So beam is moving upward. This point will be moving upward. Okay, see. So this was the beam. To draw the influence line diagram for a reaction at A, you just remove the restraints in vertical direction, not in horizontal direction, and the beam can freely move. And you have applied a unit displacement in the direction of the reaction. So see, this is your influence line diagram, and it is exactly the same as you have determined in the previous methods, right? So this is the qualitative method. You don't use any equations or anything else, and you draw the influence line diagrams. Okay. Now, for example, here it says that for shear force diagram at point C. So what it says that make a cut in the section that cut the beam here, right? You have cutted the beam. This portion is acting separately, and this portion is acting separately. Induce a relative translation at C. So induce a relative translation. This point will move upward, this point will move downward, or other way around. So as I said, the other way around, so this point has moved downward. So when this point is moving downward, this point will move upward. See, this was the original position of the beam, and this is the new position of the beam. And similarly, if this point is moving downward, so for the shear to be in equilibrium, this point will move upward of the same magnitude. So this point has moved upward. So this is the influence line diagram with the qualitative method, right? Similarly, for bending moment, it says that remove the ability to resist movement at C by using a hinge. For example, induced a hinge here, because you know that a hinge is a support, or it is a thing that can resist the reaction in vertical and horizontal direction, but it cannot resist the bending moment. And we only want to draw the influence line diagram for the bending moment, so we are introducing a hinge at support at the point C and induce a unit relative rotation. So see, you have induced a hinge. Now see, it is a hinge and you are moving it, so it will move upward like this, and this is your influence line diagram for the bending moment. So this method is much simpler and much faster and much easier, but this is a qualitative method, and it does not give you any equation or any calculation involved. Okay, but you get the main idea of influence line, right? So another example where you see both the sides or edges are overhanged, and it says, for example, draw influence line diagram for the vertical reaction at A. So you have to constrain it in the horizontal direction and just release it in the vertical direction, and apply AY and apply a unit displacement in the direction of AY. So it is moving this point to 1, for example, and the beam is like this. See, this is your influence line diagram. And another example is of cantilever beam. Okay, and it says that vertical reaction at A. So by meaning vertical reaction at A, it means that the beam will resist the bending moment. See, you have applied two rollers so that the beam cannot be what it says, like it cannot be rotated. Okay, so this is a fixed support, and you have only released the vertical reaction, not the horizontal reaction and not the bending moment. See, so when you are applying unit load, the entire beam will move to this point. Why? Because it was the only support that was resisting. So this was the influence line diagram for the beam, and it is similar to what we have drawn in the what the quantitative method, right, by using the equations and all that. So I think it is enough about the influence line diagrams. If you have any question, then you can put it in the comment section or in the queries section on LMS, and I will try to answer it. Thank you very much.